Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the class of CS352 Introduction to Soft Computing. We are discussing lecture 7, which is swarm intelligence, and today's lecture is on section 7.2, which is ant colony optimization, which is a specific technique of swarm intelligence. In the earlier lecture on introduction of this particular section or lecture, we had talked about the swarm intelligence, the characteristics of swarm intelligence, and how the natural systems have adopted the techniques of that we are going to implement in swarm intelligence algorithms. Today's lecture is about an ant colony optimization, which is a specific technique in swarm intelligence. So let us start formally with the lecture on section 7.2 ant colony optimization. In this particular lecture, we are going to talk about how ants operate in principle and what are the basic characteristics that we are interested in to form algorithms for ensemble intelligence. So first I'll discuss about the agenda for section 7.2. We'll start with the topic amazing ants, which is basically all about what makes ants so amazing and wonderful creatures. We'll then see how they are so good at reaching food. If they have a food source or some grains lying around, you'll see that ants will not only quickly reach it, but also get their whole colony out and get it transported. And the reason they are able to do this is through pheromones, and we'll see what pheromones are, the very, very basic things. And then we'll talk about the complete mechanism of how this transfer of food from one place to another is happening. And while seeing the complete mechanism, we'll try to develop an algorithm which is basically called the ant colony optimization algorithm. We'll start with its introduction, we'll then see some of its applications, and then I'll show you a demo. Basically first I'll show you a pseudocode, and then I'll show you a demo of traveling salesman problem, and finally I'll summarize and end this lecture with some extra reading materials for you. So what are ants? Ants to me are simple insects that have done wonders in the past. They are spread everywhere on the earth, almost on every continent except maybe Antarctica, or Arctic. So here are some little wonders. I'll basically call them little bodies with big wonders, and you'll be amazed to know some more details about ants. Some species of ants have been in existence for around 100 million years, while Homo sapiens or current race has been known to be on earth since about 30,000 years. So you can understand how old or ancient the ants are. Ancient, and when I mention the word ancient, I basically mean that ants have even survived the mass extinction event that was known to wipe out dinosaurs and other prehistoric animal species approximately 65 million years ago. But ants have survived that particular event. Ants are literally everywhere. Of course, unless you live in the Arctic, Antarctic, or one of a handful of remote islands, you'll likely have at least one ant species to deal with. Hawaiians have to put up with at least 50 known ant species. Although you won't probably see an ant pumping iron at your local gym, don't take their tiny size as a sign of weakness. Ants' unique physiology and their anatomy, as I'll show you in the next slide, enables them to lift objects around 20 times their own body weight, and sometimes even up to 50 times their body weight. Weaver ants are known to hold up to 100 times their body weight as well. So it's really amazing for such a small species. The important thing which is interesting for us as students of soft computing is that ants have taken the spirit of cooperation to a whole new level. As many as 50 million ants can come together to function as one highly organized and efficient colony. Ants are no dummies. one tiny ant can have as many as 250,000 brain cells. So, a colony of 40,000 ants collectively has the same number of brain cells as a human. Yet, if you look at their individual intelligence, the intelligence of an individual ant, it's quite less as compared to humans. But we'll see that they can accomplish a lot of things that probably even humans cannot. So, with that in mind, you need to be, or at least I am, in awe of these little creatures that have done wonders in the course of time. So, the reason I'm showing you the anatomy of ants is to appreciate that with such a simple body, they're able to accomplish so many complex tasks that even humans cannot. Because of their compact size and small body, they have many organs that are missing, and they cannot basically have them contained in this small body. For example, ants do not have ears. Instead, they hear by picking up vibrations via sensors on their feet and knees. Similarly, ants don't have lungs, and they actually breathe air through their skin. But with this thing, ants are actually social animals. So instead of having one stomach, they actually have two stomach, one for themselves, and the other one is basically for the larvae and the younger ones that are in their colony. And the ants can store food in their other stomach and deliver it to the correct larva or correct egg and let it breed. The good thing about ant is that ants have got excellent eyes because they have got compound eyes, and each eye is made up of many smaller eyes in turn. The ant's are very strong. They are basically able to carry a lot of weight because of the joints and the way the legs are structured. So that is the hidden reason behind ants being able to carry up to 50 times or 100 times their weight. Another thing is that ants don't really have a nose, or actually they don't smell through their nose, but instead their smell, and you'll kind of agree with me that their sense of smell is very nice and very strong. If you put a piece of food somewhere, an ant will definitely find its way and basically get its whole colony out there. So this great sense of smell comes from not through the nose but because of the antenna. And another important thing is that each individual ant colony has a unique smell. So if there's an intruder, it will have a different smell, and the soldier ants can identify the colony members by their own smell. So ants are really complex social animals. They've got a social structure just like humans have, and each class in the structure is supposed to do their own job. And each class has a specific predefined job which it performs. So at the top of the list is queen. The queen is supposed to be the reproductive powerhouse of the colony, and it is supposed to lay eggs continuously and hatch them into workers or males or soldiers. Then you have got males in the colony, and then you have got females, which are basically the workers and the soldiers. So you'll kind of realize that all the soldiers and the workers are basically females, and the soldiers are usually well built and muscular, while the workers are not as well built. The workers are supposed to do a lot of complex jobs. They are related to house cleaning, they are related to bringing food, they are related to looking after the larvae and feeding them, they are there for helping out the soldiers, etc. So there's a lot of things that workers do, and it is in the workers that we are interested in during this lecture. So I'll now be talking about how ants work, how the worker ants that are mentioned here work and find food. Ants are amazing, And when it say that one particular characteristic that stands out for us humans is how they're able to find the shortest route to their food source and bring food from their source to back, and in between they can have various stops and they can find the optimal route to the food. So keeping that in mind, we'll try to go and see how ants move and work and find reach food source and get their colony back. So in this particular scenario, what you're seeing is there are a lot of ants that are roaming around, and there's this ant nest that you can see at your left hand corner. And in the ant nest there are a lot of ants that are waiting, and the worker ants, these are the scouts that are out looking for food. So what happens is that these ants are moving around one by one, and finally a person comes, and when he moves around he has some grains, and some pieces of grains fall down, for example here, and then the person moves away. So the ants can smell it and move in that direction. As you can see that this red little puny little ant is moving around towards the grains. It finally moves towards the grains and smells and finds the grains. Once it finds them, it turns back and takes the same path back towards its own nest and informs all of its other workers that are waiting there. So with that information out to the worker ants, they'll actually start climbing out and moving towards their source, as you can see here in this particular slide, that they are now out and forming a line and moving towards the grain source. So how come that the ants are able to remember their own path? And this is the most interesting thing. Ants do not have got an excellent memory. It's not their memory that is really excellent. The main thing about ants is that they are able to release a particular chemical called pheromone, and this pheromone is something that kind of evaporates with time. So if it leaves a pheromone and that is very old, it will kind of already have evaporated and there will be no trace of it. But if there is a recent pheromone that was developed, that pheromone will have a smell, and that's because ants can smell very well, so they'll kind of follow that smell to trace back on their own path. So for example, here is an ant. When it moves, it will release a particular pheromone along the way. You can see the color is basically dark orange. When it moves a step further, it releases another point of pheromone which is also dark orange, but the previous one has kind of evaporated a little bit, and now there's very little or the power or the strength of pheromone has decreased, and with time it's going to decrease even further. So with pheromones, for example, in this example what we're going to see is if the ant moves 4 steps, it will release 4 pheromone points. The latest one will be dark orange, the one before that will be light orange, and the one at the very earliest will be very light white, or it will kind of be evaporated very soon. So with now you have got basically the background to understand how the overall mechanism works. The interesting thing about ants is that in the previous case where I showed you a simplistic case of a food particle that was lying and the ants actually smelling it and going back to their colony and bringing back help, life is not that simple really, because in general you will have multiple paths to take, and for ants it's very necessary, because they are very slow in moving. It's necessary that they always choose the shortest path. So how do they do it? The idea is explained in this particular slide. What you are seeing here is that there are ants in the nest at this end, and then you have got food at the other end, which is at a distance of A. So what ants do is there are these scout ants that are outside, and one of these ants has already visited the food as shown, and it then reaches back using the path it had taken, and it reaches back to its nest and informs the different ants in the nest. These worker ants then move out along with this particular ant and go towards the food source. However, since there are a lot more ants, they might take different routes. They will not definitely take the same route. And the way this works is that when they go out towards the food source, they'll usually take the same route, but once they're coming back, they'll have a lot of collisions, and because of those collisions, they might take a different route. For example, in the first case, you are seeing that the route was basically this one, but on the way back, when ants reached back to the food source and were coming back towards their nest carrying their food, because of the extra traffic here, some ants got redirected to this part while others continued on this track. And similarly, some ants will get routed to this track while others will continue on this track. And finally, what will happen is the shortest route, since this one is the shorter route, the one in orange, it will accumulate more pheromone quickly, while the one on the yellow side will kind of have less pheromone. Because of lesser pheromone, the yellow part will dry up soon, and there might come a time when actually no ant or very few ants will take this one, or the probability of going on these tracks will be very less, while the shortest path will have a straight line and ants that are moving on this particular path only. So ants, despite being so complex, despite being so simple organisms, yet have accomplished a very complex task. This task of finding the shortest path between 2 points is kind of something that has been problematic for humans for a while now. So while we have seen the complete mechanism behind the tracing of food and tracing their path back home, this has inspired the formulation of ant colony optimization algorithm. That is a technique it's an optimization technique to find the optimal route between 2 points, or a route that explores all the points on a given trail. So ant colony optimization is a population based SLS method inspired by aspects of the pheromone based trail following behavior of real ants. It was first introduced by Dorigo, Maniezzo and Colorne in 1991 as a metaphor for solving hard combinatorial problems such as the traveling salesman problem. ACO can be seen as a population based algorithm based on a population of agents, or ants in this case, that indirectly communicate via distributed dynamically changing information, the so called artificial pheromone trails. These pheromone trails reflect the collective search experience and are exploited by the ants in their attempts to solve a given problem instance. So, why do we study ant colony optimization algorithm? Well, we study it because it has got a lot of applications for specific problems that we consider hard to solve. So, for example, the traveling salesman problem, or if we view it from the point of view of ants, we call it traveling sales ant problem. Ants are really good at finding the solution to these problems, where they have to visit multiple nodes and find the shortest path in which they visit all nodes exactly once. And since ants are very good at it, and we are not, so we have kind of mimicked the ant behavior, and we can solve the similar problems, the traveling salesperson problem using and other problems that are related to it using the ACO algorithm, or ant colony optimization algorithm. So with that in mind, the traveling salesman problem is one application area where it can be solved. And in that case, for example, it can be applied in bus routes, it can be applied for garbage collection, it can be applied for delivery routes. We can schedule things on machine, for example, minimization of transport time for distant production locations. We can work on biological problems as well. For example, the protein folding problem can be resolved using, or has been shown to be solved using, ant colony optimization. Then telecommunication networks often use ant colony optimization to find the shortest paths in online optimization. Then airline companies use it for personal placement, and similarly the composition of products can be found by using the end colony optimization algorithm. So any problem that are of similar category can be solved using end colony optimization. We have got job shop scheduling problem, we have got vehicle routing problem, we have got dynamic problem of network, we've got quadratic assignment of problem, we have got agent based dynamic scheduling, we have got digital image processing where end colony optimization can be used to a large extent. From the ants example that we have seen earlier, there are some control parameters that we can use in our algorithms, in the ant colony optimization algorithms. One control parameter is called the number of ants. Of course, we can control how many ants there are in the simulation. Then we can also control the rate at which the pheromone is going to evaporate, and finally we are going to limit the number of iterations that are needed to accomplish the optimal or find the optimal goal. This is perhaps the most important part which we want to discuss regarding ant colony optimization. You must focus on the flow chart here and how things are changing. So you can see that this is a really simple algorithm which can be written easily by you guys, but the only issue here is that you need to define the constraints correctly and quickly, and once you get the constraints right and you have defined the search problem you have formulated the search problem correctly, then applying the algorithm is not at all an issue. So starting with the how the flow chart will work, I'll just go on with each individual step here. We start in the start state, and first of all we need to define our constraints. For example, the control parameters, we need to define those, and we need to define the search area, we need to define the initial start points for each of the ant, and then finally the objective function with which we are evaluating the optimality of our goal. Then in the next step we initialize the paths for the colony in the search area, from which node can we visit which node and what's the probability, etc. And then also we initialize the initial paths with the initial pheromone level, whatever that is, let's say 2 or whatever. Then and this initialization of pheromone is like saying that all paths are equally probable at the start, and then with the passage of time we'll kind of give more probability to the paths that are shorter, and those paths that are longer will automatically be getting less pheromone and getting lesser probability. So the next thing in the next step would be to move the ant through the source. Once we initialize the whole path, we want to move the ant through the source, and then based on the paths that the ants have taken, we like to update the pheromone density of the active path. And after updating the pheromone density, we'd like to see if the colony has finished the travel through food. If that is false, then we actually again take the next step and move the ant through the source again update the pheromone density, and again check if the colony has finished the travel through food, and we keep on doing this until we have actually finished the travel through food. In that case, if we have traveled through food and all the iterations are done, we'll actually check if the objective function for the performance has been achieved or not. If it has been achieved, then we are done. We have found the path that is the shortest one, and we return the solution, and that's it. If the objective function has not been reached, we'll reinitialize the paths again, because we might have initialized them incorrectly, and then we'll again continue with the cycle until we again have reached we have finished the travel through the food. So the algorithm, as you can see, is really simple. The pseudocode is simple, but it's getting the initial paths initialization correct, that's a bit of a problem here, and defining the constraints here, which is kind of problematic. But as you will see in the next example, at least if you can formalize, if you can model your problem correctly, if you can define your starting points, end points, and your paths correctly, the ACO is one of the simplest algorithms to apply, and that is why it is so famous and so commonly used in a lot of optimization problems. So here is a little demonstration about the ant colony optimization algorithm. I've basically taken the implementation from Kusha at GitHub, and I'm just using its jar file. On the left hand side here you can see a lot of different parameters that can be controlled. Some of them is basically the number of ants, for example. The others are the number of for example the iterations and other parameters. So this is the minimum pheromone value and the maximum pheromone value, for example, and this is the starting pheromone value, and so on. So these are the different things, and there are these 100 different points that the ants have to visit, and these are randomly generated, so they are placed randomly, and then in the next step we are going to run it for 10 iterations, and after 10 iterations we'll have the shortest path. So when you run this algorithm, and I'll show you the demo in a minute as well. This is the final result that I get after running it for the mentioned 10 iterations, and the path that it suggests is that if I, for example, if I start from here, then it goes on and 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 on like that, basically visiting, and after visiting all of them it has finally reached back to the starting point. So this is a typical travel salesman problem, and where you have to visit each point exactly once and then also reach back to the starting city or starting town, starting point. If you run it again for the same data, we'll see that the result is slightly different. So over here, instead of having two separate sections like this, it has actually gone on to move slightly different from the previous result. And you can see that the values of distance delta and the distance traveled have also changed slightly. So that shows that since this is an optimization algorithm, it will never and it is also probabilistic, so it is never going to reproduce the same results all the time. It might give you some different results as well. Having said that, let's now have a quick look at the demo and the demo software that I was talking about, and you can see here that now if I just show you the demo software instead of all these things, what we see here is that basically this is the software from the link that I just showed you before, and in here what you see is if I go here, so this is the initial pheromone value at each edge, so it is initialized by 2 or whatever. This is the number of ants. Then you have got two or three parameters, for example alpha and beta, where alpha is basically the quotient of how important a pheromone is when ant selects next node, and beta on the other hand is basically the quotient that defines the node visibility to each other. Then we have got another parameter called q, which is the number of pheromones sprayed by each ant. So it's like for each step the ant sprays like 50 pheromone or something. Then you have got the quotient of at the rate at which the pheromones are disappearing, so it's like 0.5 pheromones per move, and like 50% pheromones disappear. And then you've got the number of iterations like I mentioned before. Then you've got the minimum pheromone value, and the pheromone, it doesn't go below or lower than this, and this is the maximum one, it doesn't go higher than that, and this was specific algorithm as well again, and so on. So here you can see the different algorithms you can apply, for example ant density, ant quantity, elitist. So these are all variants of ant colony algorithms, and we'll let it be to ant colony. And here then you can select basically what kind of shape do you want. So for example you could select a circle, and if you select a circle you will see this figure. If you select random 20, you will basically, and then load, you can see that 20 random points have been generated. Similarly we can generate 100 random points, and this is how it looks like. And then you can basically select
For example, if you want to wipe these 100 out again and then load it again, so these are then different 100 points. You can select if you want it to move as per number of ants, or you could select the pheromones that are changing. We could select either of them, and in any case the number of steps C max here is kind of dictating how many what is the maximum number of iterations that will take place. So let's select pheromones for now, and let's select C max, and we are going to take this set step by step so that I see what is happening in each cycle for these 100 nodes. So let's start the algorithm for here, and once you start it, you see that the initial pheromone density of 2 is set for every node to every node, so it's a fully connected graph, and every node is connected to every other node. Then you can basically run it step by step. This is 0th iteration. We can go for first iteration, second iteration, and as time goes on, we'll see that some nodes will start or some paths will start to be more highlighted, while the other ones will be fading away continuously. So this is the effect of pheromones being dried, and as you can see now, it's kind of getting more and more clear, and some nodes are more active while others are not. And here by the 9th iteration we can see a bit of a path being formed, and finally at the end of all iterations we see that we have got the final result. So now if I select next, it's going to give me the result, and the result here is clearly that this is the most probabilistic path according to the ant colony optimization algorithm. And you can see that the time taken to compute this is 3.73 seconds, which is almost neglectable, and the distance that has been traveled by this algorithm is almost 4,583 units and or nodes, and finally the delta distance is this value. So as you can see here clearly that the whole algorithm, and let's remove the step by step, and you can kind of see the result here. If I press the start algorithm again and keep the current result in mind, we'll see that with each iteration maybe the output will change. So for example, here you can see that the output has changed now to something else, and similarly if you click it again, it is possible that it's going to change after some certain runs. Since this is probabilistic, so this is going to change, and you can see the distance delta is positive here, the distance here is negative, and so this is kind of the most feasible ones. You can run it multiple times and get the most feasible one. So this is all about this demo, and now I'll move back to the slides and continue on with the lecture. And after that I'm almost towards the end, so I'll kind of give the summary and quit the current section. So now summarizing section 7.2 from lecture 7, the ant colony algorithm. What we have seen in this particular lecture is that ants are amazing insects. They've got many extraordinary characteristics. The one most amazing task that is performed by worker ants is that they are able to find the shortest path to food, and wherever there is a food, an ant will probably be there, and soon will be accompanied by many more ants. In case that an ant has to make multiple stops, ants will basically be able to find and optimize their path for the shortest path. The ant colony optimization algorithm itself makes use of pheromones, and the concept of pheromones comes from ants, and it also uses the concept of probability to determine the shortest path. Since ant colony is an optimization algorithm, and like all optimization algorithms, they only give us an optimal solution and not the exact ones. But the main thing is that since ant colony is also probabilistic and stochastic, hence each run might give a different solution, as we had seen in the demo as well. To finally end this lecture, we have seen that the ant colony algorithm is mainly used to solve the traveling salesman problem, and is applied for solving similar category problems, and we have seen it in the routing problem, in the bus and air roots and roots in networks, etc. So we have seen a lot of applications of similar category in which ant colony algorithm is applied. We have also seen protein folding problem that if one of you probably goes on into and studies bioinformatics from me or Dr. Emmer, he might be studying the protein folding problem, or at least knowing about it, although that's not really taught in the bioinformatics course at GIK. So having said that, that is all about this lecture. You can find the additional reading slides in the next slide, and we'll discuss in the next lecture. We'll basically be discussing the swarm optimization algorithm, which is another algorithm from the same class. But what you need to know is particle swarm optimization, I think that it is called, and we'll be discussing that in a lot more detail, just like we have discussed the ant colony optimization algorithm. Thank you.